This is problems for gas law unit. Let's start right away. Okay, why is a gas easy to compress? Well, one of the ideas is that it is a lot of spaces between the molecules. Gases are easily compressed because the space between the molecules, between particles in a gas. That's actually quite correct. That's exactly what I was going to say. List three factors that can affect gas pressure. Three factors that can affect it: temperature, pressure, and amount of gas. Temperature, pressure, and amount of gas. Why does a collision with an airbag cause less damage than a collision with a steering wheel? Because the gas in the inflated airbag can be compressed, the bag absorbs some of the energy from the impact of the collision. The solid steering wheel cannot. How does a decrease in temperature affect the pressure of a contained gas? Well, it's going to be, if the temperature decreases, the pressure will also decrease. Gay-Lussac's law of directly proportional. If the temperature is constant, what change in volume would cause the pressure of an enclosed gas to be reduced to 1/4 of its original value? The volume would need to increase by a factor of 4. Next, assuming the gas in a container remains at a constant temperature, how would you increase the gas pressure in the container 100-fold? Increase the amount of gas in the container 100-fold. That's Avogadro's law. Number 7. Nitrous acid, N₂O, is used as an anesthetic. The pressure on 2.5 liters of N₂O changes from 105 kilopascals to 40.5 kilopascals. If the temperature does not change, what will the new volume be? You're going to apply Boyle's law, so it'll be PV equals PV, and you're going to solve for V2. Here we have the values plugged in. P1, V1 is plugged in. P2 is plugged in. Now we're going to gather the terms, and we're going to divide the left by 40.5, use symmetry to switch it, reading left to right, and the answer is 6.48 liters. 6.48 liters, and that makes sense. Reduce the volume, reduce the pressure, increase the volume. A gas with a volume of 4 liters at a pressure of 205 kilopascals is allowed to expand to a volume of 12 liters. What is the pressure in the container if the temperature remains constant? Okay, well, so it's going to be Boyle's law again. This time we're going to be looking for a P2. We're going to plug in P1, V1, and V2. We're going to divide the left by the right to gather the terms and use symmetry. Probably, yes, I did that. And then P2 equals 205 kilopascals times 4 liters divided by 12 liters. And the answer is 68.3 kilopascals. Okay, remember, Boyle's law is very simple as long as temperature remains constant. If a sample of gas occupies 6.8 liters at 325 degrees Celsius, what will be the volume? What will be its volume at 25 degrees Celsius if the pressure does not change? So we have constant pressure. There's the temperature change. You have to add 273. Don't forget, for gas laws, you have to change things to Kelvin. We see that it's going to be Charles' law. So here we have T1. V1 is 6.8. Here we have T2. You have to change that as well, and that's going to be 25 plus 273, that's 298. It's okay to round things. The temperature is 273.15. It's okay to round things. I do it all the time. It's just easier. So now we're going to plug in for V1 over T1 equals V2 over T2, and then we're going to cross multiply and divide 6.8 times 298 divided by 598 is going to be you'll see that the Kelvin cancels and you're left with 339 liters. This is how you should be doing your calculations. This is how you should be doing your calculations. You should be trying to prove to me that you know how to do your calculations thoroughly. Exactly 5 liters of air at negative 50 degrees Celsius is warmed to 100 degrees Celsius. What is the new volume if the pressure remains constant? Pressure is constant, volume and temperature, so this is Charles' law. So we've got to change the temperature into Kelvin. So we're going to add 273 to negative 50 degrees Celsius, and that's going to be 223. So it's going to be warmed to 100 degrees Celsius. That's going to be the next one we're going to have to change. So T1 is going to be negative 50 degrees Celsius, and T2 is going to be, it's right there, 373 Kelvin. Sorry, T1 is 223 Kelvin, not Celsius, my apologies. And then T2 is 373 Kelvin. And then plugging into the equation, V1 over T1 equals V2 over T2. And then we're going to cross multiply and divide, very simple. And the answer is V2 equals, you'll see that that's cross multiplying, 373 times 5 divided by 223 equals 836 liters. That's the answer. That is V2. You'll see that the answers are, it's very, very straightforward. It's going to become rather routine, and it just makes things flow a little bit easier. Take the time to write out the question and the answer. A sample of nitrogen gas has a pressure of 6.58 kilopascals at 539 Kelvin. If the volume does not change, what will be the pressure at 211 Kelvin? So now this is going to be Gay-Lussac's law. P1 over T1 equals P2 over T2, and there's the values plugged in. We don't need to change the temperature. The temperature is already given to us in Kelvin. So I'm going to decrease the temperature, and I'm going to decrease the pressure as well. So that makes sense. You should be able to predict certain changes just by looking at the data, and the answer should make sense. If you got 30 kilopascals, you know you did something wrong. The pressure in a car tire is 198 kilopascals at 27 degrees Celsius. After a long drive, the pressure is 225 kilopascals. What is the temperature of the air in the tire? Assume that the volume is constant. Volume constant, pressure and temperature, Gay-Lussac's law, change 27 degrees Celsius to Kelvin by adding 273. So T1 is 300 degrees Celsius, 300 Kelvin, and what is the temperature of the air in the tire? So you were given P1, which is 198 kilopascals. You're given P2, which is 225 kilopascals. So the temperature should be higher. You went from 198 to 225. Temperature increases, and you're going to be at 341 Kelvin, or 68 degrees Celsius, which is pretty warm. They say that 60 degrees should kill most of the bacteria if you're cooking your food. Personally, I would rather have it a higher temperature than that, but 68 degrees is pretty high. So a gas at 155 kilopascals and 25 degrees Celsius has an initial temperature of 1 liter. The pressure of the gas increases to 605 kilopascals as the temperature is raised to 125 degrees Celsius. What is the new volume? So we have T1 and T2. 25 degrees Celsius plus 273 is 298, and 125 degrees Celsius plus 273 is 398 Kelvin. So it looks like everything's changed. This looks like a combined gas problem. Looks like everything's changing. So PV over T equals PV over T. So 155 kilopascals is P1, 1 liter is V1, and 298 is T2. And we're going to solve for V2. You're going to cross multiply 155 times 1 times 398 divided by 298 divided by 605. See, if you don't want to use parentheses, you just hit divided by every time you go into the denominator, and the answer is 0.342 liters. So cross multiply and divide. A 5-liter air sample has a pressure of 107 kilopascals at a temperature of negative 50 degrees Celsius. If the temperature is raised to 102 degrees Celsius and the volume expands to 7 liters, what will be the new pressure? What's the new pressure? So this is you're going to add 273 to negative 50, that's 223 Kelvin. And now you're going to, let's see, we have 2 temperatures, we have 2 volumes, so we have, it looks like we're going to find pressure. What will the pressure be? So this is going to be combined gas. So there's T1, T2, and we're raising the temperature. We are raising the volume. So it looks like the pressure will be, I don't know, a little bit of each. So again, we're going to cross multiply 107 times 5 times 375 divided by 223 divided by 7. Again, if you don't use your parentheses, then you want to hit divided by each time, and the answer is, it's in scientific notation, but it need not be. It's going to be 129 kilopascals. So it went up significantly. It went up significantly. A very large temperature increase at a small volume, so the pressure went out in terms of an increase. How are the pressure and the volume of a gas related at constant temperature? Excuse my grogginess, it's 5:30 in the morning. How are the pressure and volume of a gas related at constant temperature? If the temperature is constant, the volume of a gas decreases as the pressure increases. Very interesting, very interesting. So if the temperature is constant, the volume of a gas decreases as the pressure increases. And what law is that? That's Boyle's law. If the pressure is constant, how does the change in temperature affect the volume of a gas? So this is Charles' law. This is Charles' law. And that's going to be increased volume, increased temperature. The temperature increases, the volume increases. Very, very straightforward. You see that it's being already fairly redundant. You're going to have a lot of quizzes coming up this week and next week. I hope I can get this lecture done and on the website, on the YouTube channel. What is the relationship between the temperature and pressure of a combined gas at constant volume? So we have constant volume, temperature, and pressure. Gay-Lussac's law. So increased temperature, increased pressure, and vice versa. If the volume is constant, as the temperature increases, the pressure increases. So pretty straightforward. Next, number 18. Again, Gay-Lussac's law. So far we've studied 4 laws. Boyle's law, Charles' law, Gay-Lussac's law, and combined gas law. In what situation is the combined gas law useful? Well, when you're changing pressure, temperature, and volume, when nothing's constant, as long as you only have one variable, you can do it. The combined gas law allows you to do calculations when the only constant is the amount of gas. Okay, so the number of moles is constant. They never really say that, but the number of particles is constant, and that's important for the combined gas law. Combined gas law was the brainchild of Gay-Lussac. Write the mathematical equation for Boyle's law and explain the symbols. I'm just going to let this one run, and I'll be right back. I'm going to go get a cup of tea. I'll be back and I'll see where we are. So I'll let that run, okay? Good luck. Fairly straightforward. We've been using it already, so I don't think it's a big deal. Subscript 1 represents the starting conditions. Subscript 2 represents the final conditions. Pressure, volume. What I will do is look at the timings. These problems they don't deserve all this time. A given mass of air has a volume of 6 liters at 101 kilopascals. That's pretty much air pressure, standard pressure. What volume will occupy 25 kilopascals if the temperature does not change? Boyle's law again. And I'll let this run, see if you can do the problem without me talking. Again, very important to write down questions that you have, curiosities, and bring them into class. I remember stuff like that. Those are the things that really help a student learn. I call it active learning, where you're treating the material as something that's not necessarily understandable. Part of it is, part of it isn't. But you write down questions. You want a deeper understanding than what you think might be tested. Oftentimes students say, well, I'm only going to be tested on this much of an understanding. That's all I want to learn. But that's no way to approach material. No way to approach material. So the answer for V2 is 24.2 liters. Explain how Charles' law can be derived from the combined gas law. Well, PV over T equals PV over T, and you hold pressure constant. Let's say pressure is the same on both sides, so if you can just cancel it, you can divide through by that pressure, and you come up with the equation. When the pressure is constant, the pressure terms cancel, leaving an equation for Charles' law. I'm going to reset the timings. The volume of a weather balloon increases as the balloon rises in the atmosphere. Why does the drop in temperature at higher altitudes cause the volume to decrease? Well, why does the drop in temperature at higher altitudes cause the volume to increase? The outside pressure decreases, causing a greater increase in the balloon's volume. All right, so Boyle's law, certainly what it sounds like. changes in pressure and volume. Okay. When the temperature of a rigid hollow sphere containing 685 liters of helium gas is held at 621 Kelvin, the pressure of the gas is 189 times 10 to the third kilopascals. How many moles of helium does the sphere contain? Again, this is one of the gas laws, but now we're getting into a new one, and this is the combined gas law. PV equals nRT. Not based on two different volumes, etc. This is just PV equals nRT. There's no P1 and V1 and T1. So you plug in for P and V. That's the R. R is 8.31 liter kilopascals divided by the quantity Kelvin mole, and then the temperature is 681 Kelvin. Make sure that you're solving for N, so you're going to divide the right side by the left side. You're going to divide the left side by the right side, my apologies, and just make sure that everything is in Kelvin, so 681 Kelvin, and then 251 moles, which is quite significant if you think of 1 mole as 22.4 liters. So 22.4 liters times 251, so that's quite large. It's large rigid hollow sphere. So it's pretty large. Now, 24. A child's lung can hold 2.2 liters. How many grams of air do her lungs hold at a pressure of 102 kilopascals and her body temperature of 37 degrees Celsius? Use a molar mass of 29 grams for air, which is about 20% air, 32 grams per mole, and 80% nitrogen. So PV equals nRT. Now N equals mass over atomic weight. They're saying that the atomic weight is going to be 29. That's what they mean by molar mass, is really the mass in grams of 1 mole of any particle is equal to the mass in grams of 1 particle in atomic mass units. They're talking about atomic mass units, molar mass, same thing. But they're saying it's the molar mass. In other words, it's the mass of a mole in atomic mass units. But I just say it's divided by atomic weight. It's just easier. So there's the equation, and you're going to plug in. For how many grams. So M is mass. It's not meters. It's going to be mass, and you're going to multiply the left by 29 to get rid of the denominator there, and then you're going to divide by the left. You're going to divide by what's left on the right to solve for mass, and you could flip it using symmetry. That's easy to do, not a problem. And there it is. And that's going to equal N. So N is going to be 102 kilopascals times 2.2 times 29 divided by 8.31 divided by, remember you got to hit divided by twice if you don't want to say that the bottom is in parentheses. Both are in parentheses, not individually. And the answer is 251 grams. The answer is 2.51 grams. Okay. Next. That was 24. That was a good one. Let's take a little bit of a break. You'll never know I was gone. You'll never know I was gone. What do you need to calculate the amount of gas in a sample at given conditions of temperature, pressure, and volume? Well, you need an equation. First of all, you need the combined gas law equation. What else would you need? Well, let's see. Let's see what they say. An expression that contains the variable n. Okay, well, that's correct, because what they're asking for is the ideal gas equation, not the combined gas law equation. They're asking for the ideal gas equation. 26. Under what conditions do real gases deviate most from ideal behavior? Well, first of all, there's no such thing as a perfectly elastic collision. They're going to give up heat. Real gases deviate from ideal behavior at low temperatures and high pressures. That's also very true. The ideal gas law works best, not perfectly, but best within normal conditions, within 200 or 300 degrees of room temperature. But anything in terms of extremes, and it starts to fall apart. What is an ideal gas? What is an ideal gas? Well, an ideal gas is a gas that follows the gas laws at all conditions of pressure and temperature. For instance, standard pressure and temperature is STP. You can say that it's standard and that at least the ideal gas law is constant for standard temperature and pressure. Determine the volume occupied by 0.582 moles of gas at 30 degrees Celsius if the pressure is 81.8 kilopascals. I'm going to get a cup of tea. I'm going to let you do the problem yourself. See if you can figure out the answer from beginning to end yourself. So how did you do? Did you get 17 liters? That's the way I want you to do problems, not just writing answers down. What pressure is exerted by 0.45 moles of gas at 25 degrees Celsius if the gas is in a 0.650 liter container? What pressure is exerted by 0.45 0.45 moles of a gas at 25 degrees Celsius if the gas is in a 0.650 liter container. Again, we're going to look at PV equals nRT, and there's the problem. We're going to find the pressure. We have the temperature, volume, moles, and then we have R, of course. And we're going to divide through the right side of the equation by 0.650 liters, and we're going to calculate that. 0.45 times 8.31 times 98 divided by 0.65 liters. And the answer will be, hold it, it will be 1714 kilopascals. 1714 kilopascals. Now, number 30, we have over 100 problems coming up, so this is, we're about a third of the way there-ish or so. Use the kinetic theory of gases to explain this statement. No gas exhibits ideal behavior at all temperatures and pressures. Use the kinetic theory of gases to explain the statement. No gas exhibits ideal behavior at all temperatures. In real gases, there are attractions between molecules and the molecules have volume. At low temperatures, attractions between molecules pull them together and reduce the volume. At high pressures, the volume occupied by the molecules is significantly part of the total volume. So we have the intermolecular forces become very important. Determine the total pressure of a gas mixture that contains oxygen, nitrogen, and helium. The partial pressures are: the pressure of oxygen is 20 kilopascals, nitrogen is 46.7 kilopascals, and helium is 26.7 kilopascals. And in terms of Dalton's law of partial pressure, it just simply states that you simply add the pressures. They act independently of one another, and the total pressure is going to be 93.4 kilopascals. That is from John Dalton's law of partial pressures. A gas mixture containing oxygen, nitrogen, and carbon dioxide have a total pressure of 32.9 kilopascals. What is the partial pressure of carbon dioxide if the partial pressure of oxygen is 6.6 kilopascals and nitrogen is 23 kilopascals? So the total pressure of carbon dioxide will be equal to the pressure of the carbon dioxide plus the pressures of the other oxygen and nitrogen, and that's going to equal 32.9. So subtract the sum of the oxygen and nitrogen from the other side, and you get 3.3 kilopascals as the partial pressure of carbon dioxide. In a mixture of gases, how is the total pressure determined? Well, I sort of just did it. Total pressure is equal to the sum of the partial pressures of the components, as I just demonstrated in the problem 32. What is the effect of molar mass on rates of diffusion and effusion? Well, the lighter the gas, the better it's going to diffuse. Gases with lower molar masses diffuse and effuse faster than gases with higher molar masses. Make sure you understand the word diffuse versus effuse. How is the partial pressure of a gas in a mixture calculated? Well, I think I just answered that in 33. You simply subtract the partial pressures of the other gases from the total pressure, as I did in problem 32. What distinguishes effusion from diffusion? How are these processes similar? Well, they're similar in terms of gases are moving based on energy differences and concentration differences. During effusion, a gas escapes through a tiny hole in its container. In both cases, the rate depends on the molar masses. How can you compare the rates of effusion of two gases in a mixture? Well, each of the gases, the rate of the effusion of the two gases in a mixture is inversely proportionate to the square root of their molar masses. And I'll show you that actual equation in a little bit. Explain why the rates of effusion of nitrogen gas and carbon monoxide are almost identical at the same temperature, because their molar masses are similar. Carbon monoxide and nitrogen have almost identical molar masses when the masses are rounded to two significant figures, and that would be 28 grams, or 28 atomic mass units. What happens to the particles in a gas when the gas is compressed? The particles the space between the particles is reduced. The reason they can be compressed is because the particles are far apart. Number 40. Explain why heating a contained gas that is held at constant volume increases its pressure, because the increased kinetic energy of the particles causes collisions to occur more frequently and with more force. Next. Describe what happens to the volume of a balloon when it is taken outside on a cold winter day. Explain why the observed change happens. Well, you're going to be reducing, the volume decreases, the molecules have less kinetic energy and cause less pressure on the inside of the balloon. A metal cylinder contains 1 mole of nitrogen gas. What will happen to the pressure if another mole of gas is added to the cylinder but the temperature and volume do not change? The pressure doubles because the number of particles and pressure
are proportional to one another. If a gas is compressed from 4 liters to 1 liter and the temperature remains constant, what happens to the pressure? What happens to the pressure if it's compressed? The pressure quadruples. 4 to 1 quadruples, as opposed to 1 to 4, and it would be 4 times. 1/4. Use the drawing to help explain why gas pressure decreases when gas is removed from a container with a fixed volume. As particles are removed from the container, there is a decrease in the number of collisions. Decrease in the number of collisions. That's effectively what pressure is. Write the mathematical equation for Charles's law and explain the symbols. I'm just going to let that happen and see if you can do that yourself. The gas in an enclosed container has a pressure of 300 kilopascals at 30 degrees Celsius. What will be the pressure if the temperature is lowered to negative 72 degrees Celsius? That's Gay-Lussac's law. Pressure is proportional to temperature. And now we're going to plug in to P1, T1, and we're going to calculate P2, and you're going to cross multiply and divide. And the answer is 100 kilopascals, or 1 times 10 to the 2 kilopascals. Same thing as 100 kilopascals. Calculate the volume of gas in liters at a pressure of 100 kilopascals. If its volume at 120 kilopascals is 1,500 milliliters. So make sure you can read that as well as I can relative to scientific notation. So it's going to be Boyle's law. You're plugging in and you're solving for V1. So the right side of that equation is going to be divided by 1 times 10 to the second kilopascals, and that's going to be 1.8 liters. Now, the answer should make sense relative to the changes in pressure. That's what you have to ask yourself. A gas with a volume of 4 liters at 90 kilopascals expands until pressure drops to 20 kilopascals. What is the new volume if the temperature doesn't change? Boyle's law. We're looking for V2. It should be becoming very ordinary by now. Your quizzes are going to be similar to this. You're going to divide the left by the right, and you're going to get 48.18 liters for V2, and that should make sense relative to the changes in pressure. Ask yourself that. A gas with a volume of 3 times 10 to the second milliliters at 150 degrees Celsius is heated until its volume is 600 milliliters. What is the new temperature of the gas if the pressure remains constant during the heating process? Again, 6 times 10 to the 2 is 600. Now, what is going to be? This is going to be Charles's law, V1 T1 over T1 equals V2 over T2. Believe it or not, this is precisely how I do the problems. I don't take shortcuts with my calculator. I make sure that everything is written out correctly. I've been doing this for 35 years. I've been studying chemistry my entire adult life, and this is precisely how I do it. So now I simply say, that's 150 degrees plus 273 Kelvin. That's the change for temperature, and we're looking for T2. And T2 is we're going to cross multiply and divide, and then T2 is going to be 846 Kelvin, which is 573 degrees Celsius. Write the mathematical expression for the combined gas law, which we've already calculated quite a while ago. So the fact that number 50 is well after those problems is a little strange, but nevertheless, that is the combined gas law equation. P1 V1 over T1 equals P2 V2 over T2, and let's go on to 51. A sealed container of gas contains nitrogen at 1,000 kilopascals pressure and a temperature of 20 degrees Celsius. When the cylinder is left in the sun, the temperature of the gas increases to 50 degrees Celsius. What is the new pressure in the cylinder? This is going to be Gay-Lussac's law. That's the equation. P1 over T1 equals P2 over T2. And now we're going to plug in the values that are given to us, 1,000 kilopascals over 293 Kelvin, and P2 over 323 Kelvin. So we're going to cross multiply and divide, and the answer is 1.1 times 10 to the third, or 1100 kilopascals. So just keep in mind, be able to tell right away whether or not something is one person's law or another's. Show how Gay-Lussac's law can be derived from the combined gas law. Well, very simple, and this is what it's going to say. If the volume is constant, V1 equals V2, then those two values will cancel out of both sides of the equation. For instance, if I had 2x equals 2x, then the 2x will cancel on either side, and the answer would be all real numbers. Describe an ideal gas. Well, you're going to have to describe the ideal gas in terms of the kinetic theory of gases. Now, the kinetic theory of gases says that its particles have no volume, there are no attractions between them, and collisions are elastic. An ideal gas follows the gas laws at all temperatures and pressures. We know that's a little bit weird, but either way, explain why it is impossible for an ideal gas to exist. Because the intermolecular courses have to exist. They do exist because they're made of atoms. Particles in real gases have a finite volume and are attracted to one another at low temperatures and high pressures because of those intermolecular forces. What is the volume occupied by 1.24 moles of gas at 35 degrees Celsius if the pressure is 96.2 kilopascals? They're looking for the volume. It's obviously going to be PV equals nRT. When they give you that much information and they don't ask for the same pressure or volume in terms of another set of conditions, it's definitely ideal gas laws. So V equals nRT over P. Now we're going to plug in to that equation. We're going to plug in 1.2 moles for N, etc. 8.31 liters, kilopascals per Kelvin mole. And the answer to the volume will be 33 liters. Now, that should make sense relative to the number of moles, the gas pressure, the temperature, and 22.4 for 1 mole of gas at standard temperature and pressure. What volume will 12 grams of oxygen, O2, occupy at 25 degrees Celsius and a pressure of 52.7 kilopascals? There's PV equals nRT, but it says 12 grams of oxygen gas. So the N is going to be 12 over the atomic weight, which is going to be 32. I say atomic weight. You could say formula weight for an ionic compound, and this is molecular, so you would say molecular weight. But just saying atomic weight is fine. There's not going to be some chemistry police going to track you down, so it's not that bad. There are the values plugged in, and then what you do is you calculate that out, and that's going to be 17.6 liters. 17.6 liters. Now, if 4.5 grams of methane gas, CH4, is in a 2 liter container at 35 degrees Celsius, what is the pressure in the container? Methane is going to have an atomic weight of 16 AMUs, so it's going to be 4.5 divided by 16. That will be in for N, and they're looking for the pressure, so it'll be P equals nRT over V, and now I'm going to divide that by V, and you see that the mole is going to be mass over atomic weight. So I'm going to plug into the equation and then divide through by 2 liters, and it's going to be, the answer is going to be, for P, you can see that, just kind of emphasizing that term, that's 4.5 grams over 16 AMUs, which is about 0.25-ish, a little bit more than that. That's moles. And the next step would be to do what? I'll wait. That's the answer. So you're multiplying it and then dividing through by 2. I kind of did it all in one shot because you guys should be used to it. But it's going to be the right side of the equation divided by 2 liters, and that's the answer. If 4.5 grams of methane is in a 2 liter container at 35 degrees Celsius, what is the pressure of the container? What is the pressure of the container? And there's the next step. I kind of gave you the answer and then divided it by 2. That's okay. And that's the answer, again, as I said, 3.6 times 10 to the 2 kilopascals. Okay, so it's a little bit of an emphasis on dividing it by 2. I was surprised I didn't do that. A helium-filled weather balloon has a volume of 2.4 times 10 to the 2 liters at 99 kilopascals pressure and a temperature of 0 degrees Celsius. What is the mass of the helium in the balloon? So it's going to be PV equals mass over atomic weight times RT, and they're looking for the mass. So you're going to divide, you're going to multiply PV times A atomic weight and then divide it by RT, and that will give you the mass. So I'm going to wait, I'm just going to let it play out, and I'm going to show you that derivation of the equation. See, I flipped the equation as well, which helps. That was the property of symmetry. Then I multiplied by the atomic weight and divided through by RT and came up with the mass. Correct? Came up with the mass. A helium-filled weather balloon has a volume of 2.4 times 10 to the second liters at 99 kilopascals pressure and a temperature of 0 degrees Celsius. What is the mass of the helium balloon? Let's continue. I'm bringing that equation forward for the mass. Now I'm going to plug in. I'm going to plug in to the equation. 4 is the atomic weight of helium, then 99, then 240 divided by 8.31 divided by 273 equals the mass, and the mass equals 42 grams. 42 grams. That's several moles. That's several moles, at least 10 moles, 10.5 moles, which is quite large. In your own words, state Dalton's law of partial pressure. So think about that for a minute, and then I'll put up the book's words. The total pressure of a gaseous mixture is equal to the sum of the individual pressures of each gas. That's approximately what you should get. Which gas effuses faster, hydrogen or chlorine? How much faster? Well, it's hydrogen. Don't forget hydrogen is H2, not just H. Don't forget chlorine is Cl2, not Cl. Hydrogen gas diffuses faster than chlorine gas at an approximate factor of 6. You would have to actually apply Graham's law to come up with a factor of 6. Which gas effuses faster at the same temperature, molecular oxygen or atomic argon? Well, you would have to look up the mass of argon, look up the mass of O2, which is 32, and you'll find that molecular oxygen is lighter, and the lighter the gas, the faster it will effuse. 62. Calculate the ratio of the velocity of hydrogen atoms to the velocity of neon atoms at the same temperature. Now you're going to want to put, in terms of molar mass, you're going to want to put the larger on top. So the rate or velocity of A divided by the rate of B equals the molar mass of B. So you want the B to be the heavier one, which is neon. So, and that's exactly what it is. Neon is 20. Helium is 4. So it's going to be 5 to 1. And then the square root of that. So it'll be 2.25 to 1. 2.25 to 1. And that's what it will say. 2.25 to 1. All right, 2.25 to 1 is the ratio of the velocity of neon to helium. Calculate the ratio of the velocity of helium atoms to the velocity of fluorine molecules at the same temperature. So again, this one is going to be 19/4, and the larger one we're going to put on top relative to the molar masses, and it's going to be 38/4 will be the molar masses relative to the molecule of fluorine. Okay, so it'll be 3.8 to 1. So fluorine is larger than the neon because fluorine is diatomic. So 3.08 to 1. How does kinetic theory explain the compressibility of gases? How does that explain it? Well, gases are easily compressed because there is a lot of space between the particles, and that's part of the molecular kinetic theory of gases. Use this description for questions 65 to 66. A teacher adds 1 milliliter of water to an empty metal soda can. The teacher heats the can over a flame or Bunsen burner, until the water boils, and then quickly plunges the can upside down in an ice water bath. The can immediately collapses inward as though crushed in a trash compactor. Use kinetic theory to explain why the can collapsed inward. Why didn't it explode? Boiling the water fills the can with steam. When the can is plunged upside down into cold water, the steam is trapped and rapidly condenses, reducing the gas pressure inside the can. The walls of the can are not strong enough to withstand the comparatively high atmospheric pressure, which crushes the can. It's actually a pretty cool experiment, and I will do that during class. If the experiment were done with a dry can, would the results be similar? Explain, as if you're not going to explain. The results would be much less dramatic. The change in volume and internal pressure from a heated air to the cold air is much less dramatic than with steam or vapor condenses to water, which is a liquid. Why do aerosol containers display the warning, "Do not incinerate"? I'll give you one hyphenated word, Gay-Lussac. Gay-Lussac is good for pressure and temperature, but not volume. And the volume has to be in a hard, tough container. The manufacturer of an aerosol deodorant package in a 150 milliliter container plans to produce a container of the same size that will hold twice as much gas. How will the pressure of the gas in the new product compare with that of the gas in the original container? How will they compare one container to another? The pressure will double. The pressure will double. Why? Because you are doubling the number of particles. Why must Kelvin temperatures be used in calculations that involve gases? Temperatures measured in Kelvin scale are directly proportional to the average kinetic energy of the particles. Celsius temperatures are not. Excellent answer. Please remember that. Explain how using a pressure cooker reduces the time required to cook food. Well, higher pressures, higher temperatures. Higher temperatures, food cooks more quickly. Same thing as what they said. 71. The ratio of two variables is always constant. What can you conclude about the relationship between the two variables? The variables are directly proportional, or otherwise known as direct. A 3.5 liter gas sample at 20 degrees Celsius and pressure of 86.7 kilopascal expands to a volume of 8 liters. The final pressure of the gas is 56.7 kilopascals. What is the final temperature of the gas in degrees Celsius? So I'm going through this slowly, and I'm slowly adding the data. This is the way I do it. I put the data down in tables on the side of my paper, and then I write the formula, I solve for the variable, and then I plug in, essentially. This is exactly how I do it. And then we will look for what is the final temperature. So I'm going to change everything to Kelvin, and then the final temperature I'm going to change back, because that's what they want the answer to be in. They want it to be in Celsius. And then I'm gonna same question, but now I'm going to solve for the value very slowly and very deliberately. That's the equation. This is a combined gas law equation. Well, how do you know it's combined gas law? Well, you got everything changing, plus you have two pressures. That's a dead giveaway that it's one of the other gas laws. And then the answer is 165 degrees Celsius. Look through that derivation, etc. Look through the calculations and then plug in your answer in the appropriate table. Okay. 73. Explain the reasons why real gases deviate from ideal behavior. Explain the reasons why real gases. The particles in a real gas have a finite volume and are attracted to one another. They're attracted to one another because of the intermolecular forces. How would the number of particles in two gases compare if their partial pressures in a container were identical? The number of particles would be equal, because the particular gas you have doesn't know what gas it is. So that's really big. It's identityless. Why does a balloon filled with helium deflate more quickly than a balloon filled with air? Helium atoms have a smaller molar mass than oxygen and nitrogen molecules and effuse faster because they're smaller. A certain gas effuses 4 times as fast as oxygen. What is the molar mass of the gas, the unknown gas? Well, here's the equation. You see that the velocities of each, the unknown is on top, and then the molar mass is on the bottom. And then I'm going to substitute in, and then take the square, then square both sides, and then solve for molar mass. 32 over 16 is 2. So 2 AMUs are 2 grams. Okay. Now, the next problem, the photograph shows a tube with cotton balls at each end. The cotton balls at the left were soaked in hydrochloric acid. The cotton balls on the right were soaked in solution of ammonia. When these compounds react, they form a white solid, ammonia chloride. Based on the location of the ammonia chloride in the tube, which gas diffuses at a faster rate, hydrogen chloride or ammonia? Ammonia diffuses faster than hydrogen chloride. Based on the location of the reaction product, the ammonia molecules travel about twice the distance of the hydrogen chloride molecules in the same time. How does the vacuum in the flask used to store liquid nitrogen prevent heat transfer? A vacuum contains no matter to allow the transfer of kinetic energy between molecules. Gases will diffuse from a region of higher concentration to a region of lower concentration. Why don't the gases in Earth's atmosphere escape into the near vacuum of space? The gases that make up the atmosphere, just like any other form of matter, are held near the Earth by force of gravity. What real gas comes closest to having the characteristic of an ideal gas? Explain your answer. Helium gas is composed of small atoms with little attraction for each other. Death Valley in California is 86 meters below sea level. Will the partial pressure of oxygen in Death Valley be the same, lower, or higher than the partial pressure of oxygen at sea level? Give the reasons for your answer. Higher pressure, the partial pressure of oxygen would be greater than sea level because the atmospheric pressure would be greater than at sea level. The following reaction takes place in a sealed 40-liter container at a temperature of 120 degrees Celsius. When 34 grams of ammonia react with 96 grams of oxygen, what is the partial pressure of nitrogen monoxide in the sealed container? The first thing we're going to have to do is put in the stoichiometric masses and then find the relationships relative to the number of moles. Number of moles, then you can use PV equals nRT to find the partial pressures. This is the equation. It says that there are 4 moles plus 5 moles yields 4 moles plus 6 moles. So 4 moles of ammonia plus 5 moles of oxygen yields 4 moles of nitrogen monoxide and 6 moles of water. The stoichiometric masses are 68 grams is 4 moles of ammonia, 160 grams is 5 moles of oxygen, 120 grams is 4 moles of nitrogen monoxide, and 6 times 18 is 108 grams. 108 grams is 6 moles of water. Now, next, what we have to do is we have to determine the mass of nitrogen monoxide that is going to be produced. The mass of nitrogen monoxide is going to be produced. Then we can determine how many moles are going to be produced. So the mass-mass relationship between ammonia and oxygen, the constant ratio is 4 NH3s over 5 O2s, so that's 68 over 160, and that's going to yield X over 96, cross multiply and divide, and you cross multiply and divide and you get X equals 41 grams. Now, next. There is not enough ammonia, therefore it is the limiting reagent. Okay, it's the limiting reagent. All right, limiting reagent is NH3 because there's not enough of it relative to the equation. Okay, you want to calculate the moles of NO produced. Not in terms of the stoichiometric equation, those are relative to the others, but in terms of how much, how much we did. So in other words, 4 moles is to ammonia as 2 moles is to NH3, and then it's 4 moles of NaOH from 4 moles of NO from the equation, so X equals 2. Okay, good. So far that's 2 moles. Okay. Now, PV equals nRT. All right. What I want to do is I want to get the partial pressure of that many moles from the equation. I want to get the partial pressure of that. So it's going to be the pressure equals 2 moles RT over V. Remember, this is the ideal gas equation. There's R, 8.31 liters per liters kPa per kmol. Now 120 degrees Celsius plus 273, and the partial pressure of NO is 163. And that answers the question. What is the partial pressure of NO in the sealed container? Okay, 1.63 times 10 to the 2 kilopascals. That's specifically the answer to that. Now, what about B? B is what is the total pressure in the container. So I have to add up all the partial pressures. Now I know that part of it's going to be 163 from the NO, but I need to calculate the moles of water. Well, if I have 2 moles of NO, I'm going to have 3 moles of water. Right? Makes sense? 4 is to 6 as 2 is to 3. Okay, now, so it's going to be 3 moles. So now, what I do is I go back and I find the same equation, PV equals nRT, and I find the pressure that is contributed by the water. Okay, now, so it's going to be P equals 3 moles RT divided by V. Now plug in for RT and V, and there's the ideal gas constant, 8.31, and I'm going to get, that's the equation, that's the plug-in, all right, 40-liter container, and that's going to be 245 kilopascals. But if you add that with 163, it's not the right answer, and why is that? It's a little weird. But you see, there's oxygen that was left over. Remember, the NO, the ammonia was the limiting reagent, and there's oxygen left over because oxygen was what? Oxygen was in excess, okay? Because the limiting reagent was ammonia. So if I use 2 moles of ammonia, so it'll be 2.5 moles of oxygen, right? 2.5 moles of oxygen. So now what? The experiment started with 96 grams of oxygen, or 3 moles. 2.5 moles were used, so 0.5 moles is left over. So I want to find the partial pressure of the 0.5 moles of the oxygen. So again, I'll just let this roll out, and I want to get the pressure of 0.5 moles. I'll just let this play out. See if you can get this. And that's the partial pressure of oxygen. Now add up all the partial pressures, and the total pressure will be the sum of the individual pressures, as listed here. Plug in 163, 245, etc., and then the total pressure will be and 448 kilopascals, or 4.48 times 10 to the 2 kilopascals, is the answer. Very good. All right, here are 3 plots on the same graph for gas A, B, and C for volume versus temperature. Volume versus temperature. And the question is, why are the 3 plots? The graph shows the direct relationship between volume and temperature for 3 different gas samples. Offer at least one explanation for why the graphs are not identical for the 3 samples. Hint, what variables other than temperature and volume can be used to describe a gas? Okay, we know that gases act in an ideal manner. There could be a different amount of each gas, or the gases could be at different pressures. That's absolutely correct. In other words, the number of moles could be different. One could have 1 mole, 2 moles, 4 moles, etc. Oxygen is produced in the laboratory by heating potassium nitrate. The data table below shows the volume of oxygen produced at STP from different quantities of potassium nitrate. Use the data to determine the mole ratio of potassium nitrate and oxygen reacted. So here is the data. I took the mass in grams of potassium nitrate and I converted it into moles by using 101 grams per mole. And then I converted the volume of oxygen, 22.4 into 22.4 liters per mole, into moles. And then I divided the moles of potassium nitrate to the moles of oxygen, and found that they were all 2 to 1. So the answer, therefore, to the question of the ratio of the moles of potassium nitrate to the moles of oxygen is that the ratio is 2 to 1. And all I did was convert everything to moles and then did the mole ratio. So 2 moles of potassium nitrate for each 1 mole of oxygen. Now, a 0.1 liter container holds 3 times 10 to the 20th molecules of hydrogen at 100 kilopascals and 0 degrees Celsius. If the volume of the hydrogen molecule is 6.7 times 10 to the negative 24th milliliters, what percentage of the volume of the gas is occupied by its molecule? So the total volume is going to be the number of molecules times the volume of an individual molecule, and that will be 0.002 milliliters is the total volume. Remember that 0.10 liters equals 100 milliliters, so the percentage is going to be 0.002%, or 2 times 10 to the negative third. So the next problem is if the pressure is increased to 100,000 kilopascals, the volume of the gas is 1 times 10 to the negative fourth liters. What fraction of the total volume do the hydrogen molecules now occupy? So it's the same idea as part A. You're finding the total volume, 0.002 milliliters, and then you are converting the 1 times 10 to the negative fourth liters into milliliters, which is 0.1 milliliter, and so it's going to be a smaller volume, and it's going to end up to be 2%. 2%. So that is the percent of volume that is taken up by the gas. So you see that the gas is pretty spread out. Many gases that have small molecules, such as nitrogen and oxygen, have the expected molar volume of 22.4 liters at STP. However, other gases behave in a very non-ideal manner. Even in extreme pressures and temperatures are not involved. The molar volumes of methane, carbon dioxide, and ammonia at STP are 22.37 liters, 22.26 liters, and 22.06 liters, respectively. Explain the reason for these large departures from the ideal. Because attractions between molecules in gases such as nitrogen and oxygen are insignificant, these gases have the molar volume of an ideal gas, 22.4 liters at STP. Because on their molar volumes at STP, there are attractions between molecules of methane, carbon dioxide, and ammonia. These attractions increase in strength from methane to carbon dioxide to ammonia. So the intermolecular forces are more involved in the more complex gases. What is the mathematical relationship between Kelvin and Celsius temperature scales? It's Kelvin equals degrees Celsius plus 273. A metal sample has a mass of 9.92 grams and measures 4.5 centimeters, 1.3 centimeters, 1.6 millimeters. What is the density of the metal? Well, it's going to be 9.92 divided by the product of the denominator, and that's going to be 10.6 grams per cubic centimeter. How many electron, protons, and neutrons are there in an atom of lead-206? Well, 82 protons, because that's the atomic number, 82 electrons, because that's ground state, and 206 minus 82 is the number of neutrons. Which element has the following electron configuration? Well, look at the periodic table. You see that it's going to be 3d8. So you look up what is 3d8 in the periodic table, and you're going to see that it is tungsten or wolfram. Okay, 3d8. Which element is most likely to form a compound with strontium? Which element is most likely to form a compound with strontium? Neon or is it tin? Well, tin's a metal, neon's a non-reactive noble gas, and C is selenium. I would guess selenium. Strontium, it would be actually SRSE, strontium. So it'd be selenium would be the answer to react with strontium. Which compound contains at least one double bond? Which compound contains one double bond? Is it going to be hydrosalinic acid, H2SE? Is it going to be sulfur dioxide? Is it going to be phosphorus trichloride? And which one is it going to be? Well, I'm going to go with the sulfur dioxide, very similar in shape to the carbon dioxide. Name each compound. Name each compound. These are going to be, this is nomenclature. SnBr2 would be tin bromide or tin 2 bromide, and then B would be barium sulfate, BaSO4, barium sulfate. And then C will be, let's see, that's magnesium hydroxide. And let's see if there's any more, or are we going on to 97? Let's see. Yes, iodine pentafluoride. Iodine pentafluoride. Remember, you don't use mono if it's the positive component is one positive component. You don't use the prefix mono. An atom of lead has a mass 17.616 times greater than the mass of an atom of carbon-12. What is the molar mass of this isotope of lead? 206. 206. Calculate the molar mass of each substance. Okay, let's change the timing because this is not very difficult. Okay, and that would be 158 grams, that's calcium, and then phosphoric acid would be 98 grams, and then looks like sucrose would be 342 grams, and then lead to nitrate would be 331, yes, 331 grams, and then that's it. What is the significance of the volume of 22.4 liters? It is the volume occupied by 1 mole of any gas at STP. Calculate the molecular formula of each of the following compounds. The empirical formula of C2H4O, and the molar mass is 88 grams. So it's going to be C2H4O is 44 grams. So it's going to be 88 divided by 44 is 2. So it's going to be C4H8O2 will be the molecular formula. You can see how you're doubling it. So whatever that whole number integer is, then that's going to be, you're going to multiply each subscript by that number, and that will be the molecular formula. All right, looks like we're going to have at least more than one here. Okay, the next one is the empirical formula is CH, and the molar mass is 104. So CH is 13. So let's find the multiple. 104 divided by CH, 104 divided by 13 is going to be 8. It's going to be 8. So it'll be C8H8. C8H8 will be the value for that. Excuse me, the molar mass of is 90
grams. The percent composition is 26.7% carbon, 71.1% oxygen, and 2.2% hydrogen. So I change the carbon to moles, I get 2.225 carbon. Oxygen to moles, I get 4.444 oxygen, and hydrogen, I get 2.2 moles of hydrogen. Now, after I show you there, that's that. Now I want to make up my ratios, my mole ratios. So it's going to be oxygen over carbon, and that's obviously going to be 2 to 1. Oxygen to carbon will be 2 to 1, and then it's going to be oxygen to hydrogen, which will also be 2 to 1. And you can see carbon to hydrogen is going to be 1 to 1. A little side note there. And so that's it. Those are the values. So I have CHO2 is the empirical formula, and then I know that that's 45, and then 90 divided by 45 is going to be 2, so it'll be C2H2O4, and that will be the value for that problem. Okie doke. Now, let's go on to the next problem. Here it is, C2H2O4. Now, number 101, I believe. What type of reaction are each of the following? All right, let me change the time ring here because these are getting very simple. Calcium reacts with water to form calcium hydroxide and hydrogen gas. I think I'm putting the actual equations in, so let me speed the timing up because this would go awfully slow otherwise. Okay, hold on. All right, so this is, I shortened the time frames, and this is the reaction of calcium with water, and you can see that that's the balanced reaction, and it's a single displacement reaction. What I did was I wrote the equations out because they're easier to see that what type of reaction it is. It's easier to illustrate relative to the students. So I'm just going to let this run. Tetrafluoride, tetraphosphorus decoxide reacts with water to form phosphoric acid. That was a little tricky to take. That was good. Aluminum hydroxide plus hydrogen sulfide form when aluminum sulfide reacts with water. And then the total atomic weight of C3H7OH is 60 AMUs. And I want to calculate the percent composition of 2-propanol. Aluminum oxide is formed from its elements. That's the reaction. Balance the equation. Now look at you can see that that's the lowest ratio, 432. How many grams? I'm going to put the stoichiometric masses above the reactants and products. Now don't forget, if I just calculate the mass of aluminum, I can use the conservation of mass. I can say aluminum oxide minus the aluminum is going to be the amount of oxygen. I could do that if I wanted to, or I could just do what I'm doing and just calculate the masses of each using the constant ratios. Those are the answers to the equation. Those aren't new questions. Those are the answers. Explain why a gas expands until it takes the shape and volume of its container. The motion of particles in a gas is constant, random, and rapid. Very rapid. A molecule moves extremely fast. Use the drawings to explain how gas pressure is produced. Gas pressure is produced is the result of collisions of gas particles with the container wall. That's what they are. Here is the quiz. A gas in a balloon at constant pressure has a volume of 120 milliliters at 123 degrees Celsius. What is the volume at 27 degrees? The answer is going to be B. And then C, 3/2, the original pressure. I'm going to leave you alone actually, and I want you to calculate. I want you to do this quiz, this practice quiz on your own. See if you get the right answers. And I will be back at the end of this quiz. You can of course you can put your computer on pause to see if you can do this. Okay, that's the quiz, and that's the lecture. Oh, sorry, we have 12. My apologies. Okay, and that is the quiz and the lecture on problems for this chapter on gas laws. Have a nice day.